You already know how to run Gram-Schmidt, take columns, subtract projections, normalize. But here's something you might not have noticed. Write down every coefficient you compute along the way, arrange them into a matrix. That matrix is always upper triangular. Always. Zeros below the diagonal every single time. Where do those zeros come from? That's not obvious. And the answer reveals one of the most important factorizations in applied mathematics. A equals QR. To see where those zeros come from, let's watch the Gram-Schmidt process carefully. Take 3 columns, a 1, a 2, a 3. In our working example, a 1 is the vector 1, 1, 0. A 2 is 1, 0, 1. And A3 is 0, 1, 1. Gram-Schmidt produces orthonormal vectors, mutually perpendicular unit vectors, Q1, Q2, Q3. Here is the crucial observation. Each original column is a linear combination of only the Q vectors produced so far. A 1 equals R1, 1 times Q1. That's just one term. A 2 equals R1, 2 times Q1, plus R2, 2 times Q2. That's 2 terms. A 3 equals R1, 3 times Q1, plus R2, 3 times Q2, plus R3, 3 times Q3. That's 3 terms. Each coefficient Rij equals Qi transpose times Aj, the dot product of Qi with Aj. Notice the pattern. Column J uses only Q1 through Qj. This triangular pattern of increasing terms is exactly why R turns out to be upper triangular. Now let's line up these 3 equations side by side. The vectors A1, A2, and A3 become the columns of a matrix A. The orthonormal vectors Q1, Q2, and Q3 become the columns of a matrix Q, and the coefficients arrange themselves into a matrix R. Let's see how R fills in column by column. Column 1 of R is R11, 0, 0, because A1 used only Q1. Column 2 of R is R12, R22, 0, because A2 used Q1 and Q2. Column 3 of R is R13, R23, R33, because A3 needed all 3 Q vectors. Notice the pattern. R is upper triangular. The zeros below the diagonal appear because each column of A uses only the Q vectors that were built up to that point in the Gram-Schmidt process. This gives us the famous factorization, A equals Q times R. This parallels another factorization you already know, A equals LU. Both decompositions record the steps of a systematic process as a matrix product. LU comes from row reduction, QR comes from orthogonalization, L is lower triangular, storing the elimination multipliers. Q has orthonormal columns. Both right factors are upper triangular. U stores the pivots, while R stores inner products. One key contrast, inverting L stays lower triangular, but inverting Q is trivial. Q inverse equals Q transpose. That's the power of orthonormality. 2 decomposition philosophies, 2 of linear algebra's most important tools. R is upper triangular, but why are the below diagonal entries exactly 0? This is the geometric heart of QR. Let's take a specific case. Why is Q2 transpose times A1 equal to 0? Gram-Schmidt built Q2 to be perpendicular to the span of A1. It subtracted the projection of A2 onto Q1, leaving a vector orthogonal to the entire subspace, and A1 lives in that subspace, so Q2 dotted with A1 is 0. Now let's generalize. For I greater than j, Qi was built orthogonal to the span of A1 through AI minus 1. Meanwhile, Aj lives in the span of A1 through Aj, and since j is less than I, this span is contained inside the span of A1 through AI minus 1. So Qi transpose times Aj equals 0. The chain of reasoning is Aj belongs to the span of A1 through Aj, which is a subset of the span of A1 through AI minus 1, and Qi is orthogonal to the entire larger span. Every 0 below R's diagonal is forced by Gram-Schmidt's orthogonality. by construction, not by coincidence. Let's look at R entry by entry. Start with the diagonal R11, R22, R33. These are the norms that come from Gram-Schmidt's normalization step. They tell us how long each intermediate vector Vj is before we scale it to a unit vector. Now look above the diagonal, R12, R13, R23. These are inner products measuring how each column Aj projects onto the earlier Q vectors. They capture the components we subtract out during the orthogonalization process, and below the diagonal, all zeros, every single one. These zeros are forced by orthogonality because Qy is perpendicular to Aj whenever I is greater than j, so the upper triangle holds the computation, the norms and projections that drive Gram-Schmidt, and the lower triangle holds the geometry, the zeros that encode the orthogonality we built into the Q vectors. Here's a useful sanity check. Since Q has orthonormal columns, Q transpose times Q equals the identity matrix. Now start with the equation A equals QR. Multiply both sides on the left by Q transpose. On the left side, we get Q transpose times A. On the right side, we get Q transpose times Q times R. But Q transpose Q is just the identity, so the right side simplifies to I times R, which is just R. Boxing this important result, R equals Q transpose times A. Now let's look at individual entries. The Ij entry of this product is Qi transpose times Aj, that is the dot product of the ith orthonormal vector with the jth column of A. This is exactly the inner product formula we derived in the earlier frames. So this confirms every entry of R and it gives us a direct, clean way to compute it. The reason this works so neatly is that for a matrix with orthonormal columns, Q inverse is simply Q transpose. Any matrix with linearly independent columns factors as A equals QR. Here's why this matters. The biggest application is least squares. When you solve AX approximately equals B, fitting a model to data, the QR factorization transforms the problem into Rx equals Q transpose B. Why does this work? The normal equations say A transpose AX equals A transpose B. Substituting A equals QR and using the fact that Q transpose Q equals the identity, everything simplifies down to Rx equals Q transpose B. Since R is upper triangular, back substitution finishes the job. This avoids forming A transpose A, which amplifies numerical errors. QR also powers eigenvalue algorithms through a process called QR iteration. Now here's the unifying view. Elimination sees a matrix through pivots and row operations, producing LU. Gram-Schmidt sees the same matrix through orthogonality and projections, producing QR. Both extract hidden structure from the same matrix. Both turn hard problems into easy ones. Two lenses, one matrix. That's the power of factorization.